Hello and welcome. This is going to be our lecture video for September 30th through October 1st. Hopefully you're ready to start taking some notes, but you don't have to take notes on this first one. Just tell me which do you think is the correct graph for this system right here. All right, I'll embed a question for you to pick. Correct answer. It's the one on the right. So if this is the correct graph, then the correct solution to the system is the point where they intersect. Right there, we can express it as an ordered pair, 4 comma negative 4, or we can say specifically x equals 4, y equals negative 4. All right, goal for today is to be able to graph a system of inequalities and answer different questions, or answer different types of word problems that require systems of equations. Why we could use these techniques to optimize an outcome like profit. Optimizing profit is often a systems-based problem. Okay. Your next question is which car to buy. I'm about to reveal a bunch of different options, but we need to figure out what our requirements are first. So, first off, you want a car that's less than $20,000 after a 5% sales tax is added. Okay, let's represent that first sentence with an inequality real quick. So let's define a variable. We'll say S equals the sticker price. All right, so that's what the price that's advertised, on the car's windshield and does not include sales tax. So how do I take the sticker price and figure out the total price? We'll have to apply a 5% sales tax. The trick to applying like an additional percentage is to always add it to 1. So although you're paying for a 5% sales tax, really you're paying for 105% of the car. You got to pay for the 100% of the sticker price plus an additional 5%. So that's why to add a 5%, we multiply by 1.05. So if I take 1.05 and multiply it to the sticker price, I need that value there to be less than 20,000. All right. So here's an inequality that represents this first fact. Now you want fuel costs to be under $2,000 for the 10,000 miles you expect to drive next year, and you estimate the cost of gas will be $4 per gallon. You're going to estimate high so that in case gas does go up, your budget will still cover it. So what about the car are we actually going to look at? We're going to look at the car's MPG, for miles per gallon. This is what will be advertised, and we can use that fact to figure out how much we're going to be spending in fuel. So how we're going to figure this out? First, let's shorten this to just a single letter, so we don't have to write MPG each time. We'll just say M for miles per gallon. What we're going to do is we're going to take our 10,000 miles and divide it up by the miles per gallon, and this will give us number of gallons. So that right there gives us gallons that we expect to be buying for a full year of driving. All right, we're going to multiply the gallons by the cost per gallon. So we're going to do 4 times this for $4 per gallon. And we need this whole amount here to stay under 2,000. All right, now I want to take both of these and isolate the variable real quick. So let's look at the one we just wrote. I'm going to multiply that 4 up to the top, so now I've got 40,000 divided by M is less than 2,000. I'll multiply the M to both sides. Now I've got 40,000 is less than 2,000 M. Divide both sides by that 2,000. And cross out zeros so we can do this without a calculator. 40 divided by 2 is 20. So we want M to be greater than 20. We want the miles per gallon to be greater than 20, which seems pretty reasonable. Some cars are better than 20 miles per gallon, some cars are worse. All right, and then this one here, 1.05 S needs to be less than 20,000. Divide both sides by 1.05. And I need a calculator to do that one. And we'll round down to the nearest dollar. So we'll say S must be less than $19,047. You could round to the nearest penny, but I think, if our budget is 20,000, we don't want to get, to the point where we might be like a penny short. So just rounding down to the nearest dollar is kind of always a good practice to make sure that you never come up short after sales tax or any other percentages are added on top. Okay, so now I've got two inequalities with just one variable each. This is going to help me a lot when I go to the car lot. So here is the car lot. You've got 8 options. I'm going to pause the video here for you to make a selection. Which car do you want? Okay, so there is an objectively best car here. But in order to find it, we have to compare all of these cars to our constraints. And I think a really good way to do that would be with a graph. So on this graph, I only need my first quadrant because I'm only dealing with positive values here. And I want an axis for the sticker price. I'll just write price because that's what we're seeing here. And I need an axis for the MPG, miles per gallon. So we said the important number for the price was $19,047. That was our cutoff. And we said for the miles per gallon, the important number was 20. That was our cutoff there. So I can add in some lines that cut up our graph into 4 quadrants. All right, now let's plot each of these cars relative to our constraints. So model A, it's 19.5, so it's going to be on the right-hand side of this, and it's 29 miles per gallon, so this is, we'll make a dot up here and label it A. Model B, 19,000, okay, that's on this side of our price cutoff, and 19 miles per gallon, so that's just a little bit below. Make a point there and label it B. Model C, 19,999, that's going to be on the right side of this, and up here, label that C. D will be just about there. E, way over here. F is maybe kind of like right about here. Just need to be kind of relative to the other points in the correct spot. Model G is down here and way up here. And model H, a little bit more this way, a little bit more this way. Okay, so which quadrant here did we actually want? So one way we could figure that out is with shading. So I wanted the miles per gallon to be better than 20 miles per gallon. So I wanted to be anywhere above this line. I wanted the price to be less than $19,047. So I wanted it to be anywhere to the left of this line. Well, there's only one region where these both overlap, and that's this region here. So we only want to consider cars in this region. So I only consider these cars. All right, and there's only 2 cars that ended up in there. So model G and model H both satisfy all of our requirements. So technically we could buy either of these, but I think the objective winner here is model G. How do I want to show that? We give it like a fancy border, like that. Because between these two, now we can just compare them directly. It's cheaper and has better miles per gallon. So we can use the graph to narrow it down, and then you can compare the cars within this requirement. Although there's nothing wrong with getting model H. If you just like the look of this car better, it still meets all of your requirements. So it'd still be an acceptable answer. Once you can narrow it down to which ones you shouldn't even be considering because they're outside of some constraint, then you can start just comparing them based off maybe some other metrics. All right. So hopefully we're all ready to go out and buy our first cars. Let's talk about systems of inequalities. So here's our first system of inequality. If you've got graph paper, that can make this a little bit better, but if you just got some lined paper, just to label it really well, and you can still make a pretty good graph. Okay, so there's kind of 4 things you got to remember when graphing a system of inequalities, and it's very similar to just graphing a single linear inequality, with this exception that right here you only keep the overlap. So that's kind of what we did on that previous problem. We set up 2 linear inequalities and we only kept the overlap. All right, let's do that with this one here. So we've got y is greater than negative 1/3 x plus 2. Let's review how to graph just that top equation. We put a point at its y-intercept of 2. The slope is negative 1/3, so that means go down 1, right 3, down 1, right 3, or up 1, left 3, up 1, left 3. So that's our top. Those are the dots for the top inequality. It does not have the or equal to part, so we're going to want to connect this with a dotted line. And then we're going to want to shade above this line. That's what a greater than means. All right, when you do this on your actual graph, you should shade pretty lightly. Maybe I should have said that 2 seconds ago, but shade pretty lightly because we're going to end up erasing about half of the shading. All right, let's graph the other one. It's got a y-intercept of negative 2. A slope of 1, so up 1, right 1, up 1, right 1, up 1, right 1. They do intersect at this point, but that point's actually now pretty inconsequential. At that point just kind of becomes a corner of this region. Again, I'm going to connect this with a dotted line because it does not have the or equal to. And then I'm going to shade above this line as well. So when I shade above this line, one of these regions becomes darker because it's the overlap. That's the only part that we want to keep. So only keep the overlap. So that's why we do this lightly, so we can come back with our eraser and get rid of all of this extra shading over here and over here. All right, now double check with the point. We got to pick a point that's inside here. We've got the y-axis, so maybe we'll pick something on that, like this point right here, 0, 5. I know is well inside that shaded region. Let's check and make sure that that works. So is 5 greater than 2? Yep. Is 5 greater than negative 2? Yep. That point checks out. That gives us a really strong indication that we shaded the right quadrant here. And that's systems of inequalities. It's just, it's not forgetting something like a solid versus a dashed line, and shading the correct side. Just, be diligent and then double check with a point, and I think you guys can all do this. Here's how that one looks in the answer key. You can compare it to what we did. Very similar. All right, now this corner, it's not really consequential because the solution is everything in this region, but that corner could be where we are maximizing profit or something. So it still can be useful to know where the corners of our feasible region are, in case one of those corners is maximizing some sort of objective. Kind of like what we saw with the cars. But with the cars, we actually wanted to be as far away from the corner because that meant we were getting better prices and better fuel mileage. So it's not always the case that the corner is your best spot, but it's still useful to know where it is. Anyway, let's try another example with absolute value. Here's our two inequalities. Let's graph the top one. So you just kind of graph them separately. Ignore the fact that they're a system for a little bit and just go to work graphing. So this is a linear equation with a y-intercept of 3 and a slope of 2/3. So turn that into rise over run. So up to right 3, or back to our main point, down to left 3. Down to left 3. Oh, left 2, there we go. This has the or equal to part, so I want to connect this with a solid line, showing that points exactly on this line do work to solve that top inequality. And then this is a less than, so less than, I shade the lower side of this line. Let me pick a lighter color here. All right, so shading down here. All right, on to our next one. Here, this is going to be a V-shaped graph that's been shifted up 1. So I've already memorized my parent function for a V-shaped graph. It's just got a vertex at the origin. Now that's been shifted up 1. The slopes on the side are 1 and -1. This one should be connected with a dotted line because it does not have the or equal to. All right, and then greater than means shade above this line. So what happens when I shade above that line? Let's do another color. So I'm shading above this V shape. I'll see one section gets darker. Is that triangle in the middle, and that's the only part that we keep. I'm not going to erase everything else, but we only keep this. All right, so only ordered pairs inside of that region are going to satisfy both inequalities. Let's double check with the point 0, 2. So is 2 less than or equal to 3? Yep, that works. Is 2 greater than 1? Yep. So shows that we've shaded the right region, just that triangle in the middle here. All right, let's go the other direction. Here we've got a shaded rectangle. Can we write a system of inequalities to describe this? So we got to link them all with a curly bracket, and I need space for at least 4 to represent these 4 sides. The horizontal lines can be represented with y equals equations. So I could do something like y is less than or equal to 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. For the top boundary, and then y is greater than or equal to -4 for the bottom boundary. X is greater than or equal to -1 for the left boundary, and x is less than or equal to 3 for the right boundary. And there's my system of inequalities that describes this. Let's try it again with this graph. So need a curly bracket with space for 3 inequalities here. Let's look at, we'll do it in the matching color. We'll do the blue line first. This needs to be a y is less than. It's a dotted line, so it doesn't get the or equal to. And now what's that slope? That looks like a slope of 1/3, so 1/3 x, and then the y-intercept is 4, plus 4. All right, now for the red line, this is going to be a y is greater than or equal to, because the shaded region is above, and this is a solid line. Let's see, that slope looks to be a slope of -3, so -3x, and a y-intercept of -1. And on for the green line, y is, again, this is a greater than or equal to. Look where the shading is relative to the line. This seems like a slope of, probably hits right there, so that's a slope of 1, 2, 3, 4, 5. So 5x and a y-intercept of +1, plus 1. All right, there is my system of inequalities to get this graph here. All right, on to a slightly different topic. We're going to be talking now about word problems. Starting with this one right here. I have $6 and 42 coins. What possible combination of denominations could I have? Here I'll pause the video and let you list out as many as you can come up with. Okay, now what if I restrict it a little bit more? What if I say I can only have quarters and dimes? Can we come up with a combination that still is worth $6 and contains 42 coins? So the first thing we need to do is define some variables, and we've got to be very precise with how we define these. I want Q to be equal to the number of quarters. So now don't just say Q equals quarters, because then it's a little ambiguous. You could say, well, is it the value of all the quarters? Is it the cost of 1 quarter? Is it something else? The weight of the quarters? You know, we don't know. Number of quarters. This is now nice and explicit. Now we'll do the same for dimes. D equals the number of dimes. Now I need to represent these two facts, that I've got $6 and 42 coins, with these two variables I just came up with. We'll do the easier one first, the 42 coins. If I have 42 coins, then the number of quarters, Q, plus the number of dimes, D, must add up to 42. Simple as that. 42 equals Q plus D. Number of quarters plus number of dimes. Now on for the slightly harder one, the $6. So to get $6, I have to figure out the value of all the quarters and then add that to the value of all the dimes. So what will take the number of quarters and turn it into the value of the quarters? Well, that is to multiply the number of quarters by their value of $0.25. So 0.25 Q, now this piece right here gives me the value of the quarters. I'll write that off to the side. This is the value of just quarters. All right, let's just test it real quick. You know, if I've got 8 quarters, 0.25 times 8 is 2. 8 quarters, is that worth $2? Yeah, that makes sense to me. All right, and now we're going to add that to the value of just the dimes. So that we take dimes and multiply them by their value of 0.1. Add these together. We should get up to 6. All right, we have 2 missing variables. That means we need 2 equations. I've got my 2 equations. This should be solvable. So now we just have to pick a method to solve it with. I think the easier method here would be elimination. So I'm just going to copy down this first equation, 42 equals Q plus D. But for this top equation, I'm going to multiply by something that's going to give me a 0 pair. I'm going to multiply by -4. So I got -24 equals negative Q, there's my 0 pair, minus 0.4 D. All right, here's my system. We've got the 0 pair, let's add it together. On this side, we get 18. Over here, the Q's cancel. And I'm left with 0.6 D. Divide both sides by 0.6. And I get 30 equals D. So we have 30 dimes And if we have 42 coins total, that means we must have 12 quarters. We'll show that by plugging the 30 in for D in this equation here, subtracting the 30, we get 12 equals Q. All right, because this is a word problem, we should answer with a sentence. So I have 12 quarters and 30 dimes. Let's make sure that that makes sense. So 12 quarters, what would be the value of 12 quarters? Well, that would be $3. 30 dimes, that would also be $3. $3 plus $3, it adds up to $6, just like we wanted it to. All right, so what should we box? We should box this sentence here. I have 12 quarters and 30 dimes. All right, another word problem. The admission fee at a small fair is $1.50 for children and $4 for adults. On a certain day, 2,200 people enter the fair and $5,050 is collected. How many children and how many adults entered? All right, so we need to define some variables. We'll say C equals number of children and A equals number of adults. So again, I'm very explicit here. Now I'd say C equals children because then it's ambiguous. What about the children? Well, specifically the number of them. You know, not like all of their heights added together or something like that. A equals number of adults. All right, now 2,200 people entered, so that's an easier one to write. 2,200 equals C plus A, number of children plus number of adults, is 2,200 people total. Now $5,050 was collected, so we have to multiply the number of children by how much they're paying and the number of adults by how much they're paying. So 1.5 C plus 4A, that gives you the, how much all of the children paid together, how much all of the adults paid together, add them together. We've got $5,050. From these two facts, we can solve for C and A. We've got two missings, two equations. That's the setup we need. So how about I'll take this equation, I'll multiply it by -4, and write it below this equation so that I get a zero pair with the A's. So that gets me -8,800 equals -4C minus 4A. Add these together. I need my calculator. And we got 5,050 minus 8,800. -3,750 equals -2.5C. And these cancel out. Divide both sides by -2.5. Divide by -2.5. I get exactly 1,500, which makes sense to me. Given that there's 2,200 total, 1,500 of them were children, and that means that there must have been 700 remaining to be adults. So 700 equals A. And we enter with the sentence, there were 700 adults and 1,500 children. So a lot of supervising had to happen that day. Okay. And we could plug it back into the cost one to make sure that we make our 5,050 with this combination, but I'm pretty sure it's going to work. Okay. Next question. A passenger jet took 3 hours to fly 1,800 miles in the direction of the jet stream. The the return trip against the jet stream took 4 hours. What was the jet speed in still air and the jet stream's speed? So you might have noticed this if you've ever flown round trip to a city, is that one leg of the trip took longer than the other, and that's because of these things called jet streams, which are kind of prevailing winds up high. And when you're flying with the jet stream, your ground speed's a little bit faster. When you're flying against it, your ground speed's a little bit slower. So we need some variables here. We got to define them very precisely. So we'll say J equals the jet's speed in still air. So if the wind wasn't blowing at all, how fast would it be moving over the ground? And then W equals wind speed. Okay, so when you're going with the wind, you get to add these together because the speed in the still air gets to add to the wind speed to come up with your new ground speed. You're going even faster over the ground because the wind is moving over the ground and you're moving through the wind. All right, when you're going against it, you have to subtract the wind speed from the jet speed in still air. All right, so to create my equations, I want to take that 1,800 miles and divide it by my speed. We'll say when I'm going faster, it's J plus W. All right, and then you take your distance divided by your speed. You should be left with the time. When I was going faster, it took 3 hours. So 1,800 divided by J plus W equals 3. Now 1,800 divided by J minus W. Here we're taking the wind speed away from the jet speed. We go slower and we get 4. All right, here's my two equations, but they're, kind of difficult to work with. What I want to do is simplify by multiplying this side by J plus W and this side by J plus W. And over in this one, I'm going to multiply both sides by J minus W. This should help me get rid of all of my fractions. So now the left-hand equation is going to be 1,800 equals, and I'll even distribute the 3J plus 3W. And this one over here is going to be 1,800 equals 4J minus 4W. Okay, now at this point, I think we can get a zero pair, but we're going to have to multiply both equations. I'm going to multiply the left equation by 4, and the right equation will multiply by 3. So I'm multiplying them by the opposite coefficient. I'm actually focusing on W because I've got a negative there. It's going to help me make that zero pair. And here a calculator could be useful again. 1,800 times 3 is 5,400 equals 12J minus 12W, and 1,800 times 4, we've got 7,200 equals 12J plus 12W. Okay, you've got a zero pair there, so let's add these together. So I'll add that to the 5,400, we get 12,600 equals 24J, and these canceled. Now I divide by 24, and then I get 525 equals the speed of the jet. Now we look for an easy spot to plug this back in. I probably won't go back to one of those original equations. I'd rather plug it in somewhere like right there. So let's take that, multiplied by 3. We get 1,800 equals 1,575 plus 3W. Now we'll do 1,800 minus 1,575 and we get 225 equals 3W. Divide by 3, and we get 75. All right, now it's very important how we say this answer. So the airspeed of the jet is 525, and we got to give it the correct unit, miles per hour. And the wind speed is 75 miles per hour. So we say airspeed. If you say ground speed, then that's not accurate because the ground speed actually changes depending on if you're going with the wind or against the wind. Airspeed is constant at 525. And that's why we have such different, the 75 miles per hour wind is why we have such different times for the different lengths of the journey. Okay. I'll embed a few more questions here, but that does it for this video. Have a good rest of your day.